Chapter 8. Chapter 8 is on internal flows due to forced convection. For this, let's briefly revise on what you have learned in fluid mechanics. So let's say you have a fluid flowing in a pipe of a diameter, say R0, okay, and R varies from the central axis. And we've seen in the external flow chapter as well is that whenever a flow moves over a surface, there is a boundary layer created due to the no slip boundary condition. So if the wall is not moving, the fluid just above it won't move, and that will create a boundary layer due to the viscous motion or due to the viscosity of the flow. And if you have an enclosed flow or an internal flow, you will have boundary layers on all across all the boundaries. So we are looking at a 2D cross section of a circular pipe, that's a cylindrical pipe, and in this cross section you will see a boundary layer being created from the surface on the top and from the surface on the bottom. And uh, these two boundaries will eventually merge, and then beyond that point you'll have what is called as a fully developed flow. So what happens is that your velocity profile at the entry will be uniform because your inlet velocity is uniform, and you see as the region which is your entrance region or the hydrodynamic entrance region, you'll see that your velocity profile gradually increases, and then there's a flat straight line, which means that the velocity here is still the same as your entrance velocity. And then again you'll have a curvature or a gradually increasing velocity in the lower boundary layer as well. And this flat portion of constant velocity decreases gradually as the boundary layer increases and goes away as the two boundary layers merge. And this distance here is denoted by xfd comma h. That means the distance at which the flow is fully developed, and h stands for hydrodynamics. So you'll have the same thing for a thermal boundary layer as well. And beyond this location where the flow is fully developed, you will have a parabolic profile. And uh, in this region, your velocity u is now not a function of x and r, but it's just a function of radius. That means even if I draw a boundary here, this profile here will be same as this profile here. So your velocities will not change in the x direction, which is this direction right here. It will only change in the radial direction. So what this means is that uh, for your now what we've seen is that for your hydrodynamic boundary length, which is denoted by xfd comma h, your when your x is greater than this value right here, it's the flow is called as the fully developed flow. And because we are looking at a flow in a single direction, our velocity in the y direction is 0, so we don't have any velocity in the radial direction in this case. So we just have velocity in the x direction, the flow is moving in the x direction. But what happens is that because our velocity in the fully developed region is just a function of r, we can say that our du by dx is equal to 0. That means our velocity is not, or x velocity is not changing with respect to x. Now let's define the Reynolds number for these types of flows. The Reynolds number will be um into d. Our characteristic length will be the diameter of the pipe times the viscosity divided by the viscosity. And this here is very important to note is that the critical Reynolds number for internal flows is 2300. So if your flow is smaller, if your Reynolds number is lower than the critical Reynolds number value of 2300, 2300, your flow will be laminar. And if it's greater than this value right here, then your flow will be in the transition region, and it may uh, be a turbulent flow, or it may take some time to completely become into a turbulent flow. But for your flow to be laminar, your Reynolds number has to be lower than 2300. So there are a few empirical relations that you must know. So the first one is, if you are in the laminar region, or if you have a laminar flow, you can calculate, if you have laminar flow, you can calculate your hydrodynamic boundary length, okay, or the location at which a location where your flow will be fully developed by this relation here. So it will be, so your x by d for a laminar flow is nearly equal to 0.05 times the Reynolds number for that particular diameter. And this here is the relation for if your flow is turbulent. So if your flow is turbulent, your xt can, or your fully developed boundary length can be anywhere between, it will be between a range. So it will be somewhere between 10 times d and less than 60 times d. Okay, so these are two empirical relations that you must know. So now if you notice here that we don't have in the definition of our Reynolds number, we don't have u velocity, which is our inlet velocity, but instead we have taken a mean velocity. And why we'll see why we've taken a mean velocity. That's because after our flow is fully developed, we don't have a uniform velocity of u, but we have a profile of a velocity which changes with radius. So that's why we need to assume some average or a mean velocity to define a Reynolds number. Now, this mean velocity can be related, or is related to the mass flow rate m dot that's coming into the pipe. And we can write the mass flow rate as the density times the mean velocity times the cross-sectional area. So if so, how will you find your mean velocity and the area? So if you take a small cross section, you can write your mass flow rate as your density times the velocity at a particular location and r times the cross sectional and integrate it with respect to the cross sectional area. And this will give you the u mean, or the mean velocity, as 2 divided by r0 square, integration of 0 to r0 of the velocity ur comma x. But we know that if it's fully developed, our velocity will just be a function of r times r dr. And how did we get the r dr here? We can write our cross-sectional area as uh, we can write a cross-sectional area as pi r square. So if we do a DAC, we'll get pi times d of r square, which will be 2 pi r dr. So this is where we get our rdr from. And remember, this relation for u mean is true for a circular tube. So we've assumed that our tube, or our internal flow here, is occurring in a circular tube. This can you can have internal flows in rectangular ducts, which you see in a ventilation system. So you have ducts going all around the building in for your ventilation, which carry cold or hot air. So those ducts usually have a square or a rectangular cross section. So that's why you must note that this relation here is for a circular tube. So similarly, we can look at a thermal boundary layer as well. So we've seen in chapters 8 and sorry 7 and 9 that whenever we have a temperature difference, even for a natural convection or a forced convection, there will be a thermal boundary layer that will be created. So in this particular scenario, let's say that we have a same pipe, and the surface condition at the pipe are that the pipe is at a surface temperature of Ts, which is greater than the fluid temperature. And we may also have another condition, which is that we may have a constant heat flux. So these two here represent two different conditions, which we will see which we will see how we can apply it into our equations. And again, the thermal entry length relation for a laminar flow for this particular for our thermal consideration will be 0.05 times Re, that's the Reynolds number, times the Prandtl number. So we have the Prandtl number here, and uh, note that the uh, thermal entry length here has a subscript T, which stands for thermal. So in the previous scenario we had an H which stood for hydrodynamic, but we have a T here. Now in this case, if you notice that uh, because we have a temperature difference and there's heat being transferred continuously along the x direction, our temperature profile is not constant as we move in the positive x direction. So our temperature profile here is different than the temperature profile here, although we are in the fully developed region. So that means um that we cannot say that our t is just a function of r, because it's changing with respect to x, unlike the velocity, where for velocity our du by dx was 0. So in this particular case, we will need some quantity which we need to define that does not change with x in the fully developed region. So for that, let's uh, let's first define a mean temperature so that we know where to calculate the uh, properties at. So the mean temperature of the fluid has a relation which is this. So it's rho divided by density of the fluid divided by m dot Cp. That's the specific heat at constant pressure, and integrating it over the cross-sectional area. We are integrating the velocity, which is the function of r, and the temperature at that particular location, which is a function of r. So at a particular location, at a particular x, our temperature is just a function of r. But if you look at the overall temperature distribution here, it will be a function of x and r. So we are looking at a particular location. So our uh, mean temperature here is a function of velocity and temperature, whereas our mean velocity was just a function of ur. So that's one difference. So we can simplify this and write it as Tm equals to 2 by um r square, r0 square, r0 being the radius of the pipe, and integrating u times t times r with respect to dr from 0 to r0. So if you're asked to calculate the mean temperature, this is the formula that you will use. Now we know that the heat that's transferred, or the heat flux, uh, can be calculated by Newton's law by H times Ts minus Tm, Ts, let's say that our Ts is a constant value. Our Tm now here is a function of x. So you will have a different mean temperature for this location compared to a compared to a mean temperature at this location. So you'll have the mean temperature will be changing as you move along the x direction. So uh, as I said that we need some quantity uh, that should remain constant with respect to x, uh, like which will give us a relation something similar to du by dx that we had in our hydrodynamic boundary layer. So we define the dimensionless temperature axis. This is similar to what we've seen before, and I'll say that my T star is Ts, that's the surface temperature at that location x, minus the temperature of the fluid divided by the temperature at the surface minus the mean temperature of the fluid. Okay, so this definition of T star is different from the excess temperature definition that we had in the fins for the fins. So do not confuse that definition with this definition. And if you see now, your T star will not be a function of x, and you can write your del T star by del R. This will mean that your del T star by del R, that means your variation of T star with respect to R, will also not be a function of x. So let me repeat myself. If you have a fully developed thermal boundary layer, if you have a fully developed flow which is thermally fully developed, these are the conditions that your T star must follow. So your uh, T star must not be a function of x, and your del T star by del R obviously must not be a function of x. So excuse me, that means that your del T star by del x must be equal to 0. Now this means that your, if I replace the definition of del star from here into this is the equation that I get. So to satisfy this condition, I have an equation which states that um, for a fully developed thermal flow, my dt star by dx is equal to 0, and substituting the value of t star, this is the relation that I get, and I'll call this as equation 1. Okay, let's move on and let's see if we can find relations between the temperatures and the mean temperatures for the two boundary conditions that we looked at. That's the constant heat if our pipe, if the walls of the pipe are at a constant surface temperature, or if they are subjected to a constant heat flux. So how will our uh, temperature gradients look like? So let's say if I take a control volume at the pipe wall. So I think I've drawn the control volume wrong. So let's say if this was the wall and if I've drawn a control volume here, and if this was R naught, I can say that uh, my Q being conducted through the wall is what is being convected into the fluid. Okay, so that's what I've written here. And my Q conduction can be defined as K into del T by del R at R is equal to R naught, that's the wall, is equal to H times Ts surface temperature minus the mean fluid temperature. I can write this as H by K equals to del T by del R at R is equal to 0 divided by Ts minus Tm, and I can see that this is not a function of f of x. So we can say that in a thermally fully developed flow with constant properties, which means if your k is constant and if your h is constant, sorry, if your k is constant for constant properties, the local convection coefficient is a constant and independent of x. So if you have constant properties and your temperatures, so we've seen that these temperatures are not a function of x, that means that your h will also not be a function of x. So let's look at our first boundary condition, which is the constant heat flux. If we have a constant heat flux at the surface, so this means that our qs will be not 0 but a constant. If it's a constant, I can write, if I differentiate this by anything, it will give me a 0. So I am differentiating my qs with respect to x, which will give me a 0. I'll substitute the definition of qs from here, and I can say that because h is constant, h times d of ts minus tm by dx is equal to 0, and this will give me this relation right here, that dt ds upon dt d of ts by dx minus d of tm by dx will be equal to 0. So by taking the dtm by dx on the other side, we get this relation, and this is true for the fully developed region. So now let's take the equation that we had in our previous slide, which we had assumed for, which we had solved for the fully developed flow, and substitute these values in that equation. Substitute this value right here, and this is the relation that you'll get. You'll get your temperature at any location with respect to x will be equal to the variation of mean temperature with respect to x in the fully developed region. Okay, so this is one relation that we've got for the constant heat flux if you have constant heat flux at the surface, and doing a similar analysis, you will get another relation for a constant surface temperature, which will be your variation of temperature with respect to x in the fully developed region will be equal to Ts minus T divided by Ts minus Tm times the variation of, or dTm by dx in the fully developed region. So we will use these relations to derive the temperature profiles or the temperature distribution, but I just did this exercise so that you understand how our relations or how our temperature gradients will be different if you have different conditions at the surface, and how it's important to identify what the surface of the pipe is before you start your analysis.